In this Solidity tutorial, we're going to be building our own product on top of the Lego bricks of DeFi. We're going to be interacting with external contracts such as Chainlink price feeds and Uniswap version 3 to create a vault. The purpose of the vault is to manage a 60-40 portfolio where 60% of the portfolio is held in cryptocurrency and 40% of the portfolio is held in stablecoins. This is an intermediate tutorial, so I'm going to be going quite fast and glossing over some of the basics. There's an introduction to the Solidity linked to above. I'm going to be focusing more on the tooling that can be used to test and create Solidity contracts and interact with external contracts to build real-world products. I'm going to be using Hardhat, which is a framework for building and testing and deploying smart contracts on Ethereum and other EVM-compatible blockchains. I'm a big fan of Truffle, but I feel that Hardhat is more expansive and the scripting language is really hard to beat. It also has some great features like being able to fork the mainnet or one of the test nets locally. We'll get more into that when we get into the testing section. To run this, you're also going to need a JavaScript runtime environment, which is called Node.js. Most of you should be familiar with that. And then we're going to need an Alchemy API key. This is free for basic usage, and it's kind of, if you're coming from a Truffle environment, it's the same as an Infura API key. It gives you access to a node on the Ethereum network. All the code that I write here is going to be open source. It's available in a link on the description. There's also a blog post which goes into more details. Bear in mind that this code is for demonstration purposes only. It was written for the purpose of this tutorial, and shouldn't be used on mainnet for real financial transactions. So if you want, you can go ahead and clone the GitHub repository. You can work for the files locally. We're going to move it into the repository and run npm install, which will install all the dependencies, including Hardhat. Now let's have a look at the Hardhat configuration file. This is a hardhat.config.js. And I've got a couple of requirements here. We're going to import ethers, and I'm importing a credentials file. We can see this example file here. We've got room for an Alchemy API key, a private key, and an address for the account. You can get this from MetaMask, or you might want to generate your own just for testing purposes. Then we've got an Etherscan API key, which is used for verifying that contract. We've then got some exports. We've got two networks. We've got the Kovan network, which is a test network on Ethereum. We've got the private key imported from the credentials. And then we've also got a local network, which is just a local host, the computer that I'm running this on port 8545. We'll be running Hardhat node here to start up our own local node later on when we're testing. Finally, we've got an export for the Etherscan API key. All pretty straightforward, so let's move on to the vault. So I'm not going to embarrass myself by live coding here, but I'm going to go through each section and talk about the design decisions that I made when writing this contract. So first we're doing this in a GPL license identifier. Then we're using Pragma Solidity 0.8. And this is significant because in version 0.8, the core Solidity team introduced some fixes which prevented integer overflows and underflows. This somewhat removed the need for SafeMath, and I won't be using the SafeMath library in this contract. I haven't actually tested this much myself yet. If I was going to put this into production, I want to do some pretty robust testing of those native safety features. We then got some standard comments, the title, license, author, and a notice. We're importing the Hardhat console, which lets us do things like console log inside the contract when we're running it locally. We're going to import some OpenZeppelin libraries for ERC20 interfaces and Safe ERC20 for doing safe transfer and things like that. We're also going to be using some Uniswap v3 contracts, ISwap router and ISwap quota. The router is what we use to actually carry out swaps or trades on Uniswap v3, and the quota is going to be used as a price oracle to get the price directly from the exchange. We've also got a custom interface here, which is just used for the Chainlink oracle. We've got an additional function on the ISwap router interface, which is refundee function. We just call it at the end of a swap. And then finally, we've got a depositable ERC20, and this is for WETH. So with wrapped Ethereum or WETH, what happens is it's a standard ERC20 contract because ETH on its own, the standard native token of Ethereum, isn't actually ERC20 token, so we can't use it in the same way as an ERC20. So what we do is we deposit ETH to the WETH ERC20 contract, and it has this custom deposit function which allows us to do that. It also has a withdraw function which we're not going to be using. So basically all we need is a standard ERC20 with this extra deposit function for that. Let's take a quick look at how we can kind of find these functions and create these interfaces so that we can interact with external contracts. So if we take the WETH contract address here, and these are the Kovan addresses, and let's go to Etherscan. I actually want kovan.etherscan for the Kovan testnet. Zoom in right here so you can see. Let's paste that contract address in. If we go to contract, we've got this little tick box, which means it's verified. And we can go to write contract. We can see we've got some of the standard ERC20 functions like approve, transfer from. We've also got these deposit and withdraw functions. And we can actually interact with this contract directly from MetaMask. So if we open this up, let's sign into MetaMask. Connect to Web3. Okay, we're connected. Now let's deposit 0. Let's just make sure we're on the testnet for sure. Before I do something silly. We've got COVID testnet, we've got a little bit of funds here, so let's deposit 0.001 ETH into this ERC20 contract. And what that's going to do is it's going to send us WEF back. Now what we can also do is go and have a look at the code. If we scroll down, we can see we've got this function deposit public payable function here, and that gives us the framework for our interface. So if we go back to the code, we can see that this is pretty much the same as this. The only difference is with an interface you have to use external rather than public. But you can see that this top line here, which forms the instructions for how to use an external contract within our Solidity code, is very, very similar to the top line of the function here. And if you take a look at some of these OpenZeppelin contracts, these guys are the experts on how to create these interfaces. They've been audited by just about everyone in the industry. Okay, so scrolling back down, let's get into the contract. So we're declaring MyVault as a contract now. We're going to create a version number, which is just version 1. And then we're going to create a list of hard-coded Kovan addresses. I'm not going to be deploying this to mainnet. I'm only going to be using the Kovan testnet. You could potentially put these into the deployment configuration and you could pass them into the constructor function. That's a better way to do it if you're going to be deploying to multiple separate networks. Here I'm only really going to be using Kovan, so I'm just going to hard code the addresses in. So I've got the DAI address, which is a US dollar stablecoin, WEF, which is wrapped Ethereum. I've got a Uniswap quota address and the Uniswap router address. These are the interfaces for Uniswap that we declared earlier. I've got a Chainlink ETH USD address. I'll just pop this into Etherscan as well, so you can take a look at this contract. And if we go to contract, we can just go to read and get the latest answer. And what it basically does is give us a price for Ethereum. It's that simple. This is on testnet, so the price won't be accurate. If we go to docs.chain.link/docs Ethereum-addresses, you can see there's different price points for lots and lots of different markets. And Chainlink provides these data price feeds as an Oracle service. If we go to any one of these, we can go to the contract, read contract, and get the latest answer. Bear in mind these aren't live prices, and it's always a good idea to check the latest timestamp as well. So once we've declared our external addresses, we're also going to declare some state variables. We've got the ETH price, which is currently set to 0. This will be updated by our oracles. We've got USD target percentage, just as a custom variable. I've got it set to 40, so I'm going to have 60% of the portfolio in Ethereum and 40% in the DAI stablecoin. The USD dividend percentage, so I've got this set to 25%, which is basically you can draw down 10% of the overall portfolio per period. The period I've got is currently 3 minutes for testing. You probably want to change this to maybe once a year, so you can draw down 10% a year from the contract. And this would be useful if you want to set up something like a perpetual fund for your kids or a charity or something like that. We've got a next dividend timestamp that's set in the constructor. And we've got an owner address, which is also the address that deployed the contract, where you're going to need some funds to pay for the gas fees to deploy the contracts. And that's the owner address, which actually owns this contract. We're using Safe ERC20 library for both the standard ERC20 interface and the depositable ERC20 interface. Then we're declaring our actual tokens. So the DAI token is just a standard ERC20, and then the WEF token is a depositable ERC20. They're also going to declare the quota variable to be the Uniswap quota, and then the Uniswap router to be the Uniswap router interface. And then we're going to use a pretty ugly event log, which is just an example of how to use events. And we're going to declare that MyVault log takes a string and a reference, and that'll be logged to Etherscan and other tools which can log those transaction events. The construction function, as I'm sure you already know, is only run once when you deploy the contract. And all we're doing here is we're setting the variables for the next dividend timestamp to be the block timestamp, which is the Unix timestamp, or the number of seconds since January 1970, plus the dividend frequency, which is the number of seconds in 3 minutes. And then we're also going to set the owner to the message.sender. So the owner address is set to the deployer of the contracts. We then got two functions here, which might be a bit overkill, but we're just basically getting the DAI balance and getting the WEF balance. These return the balance of those ERC20 tokens. So now we've got the get total balance, which is a public view function, which returns an unsigned integer. We've got our first example of a require statement here, and this requires that the Ethereum price is set to above 0. Remember, we set this ETH price value as 0 in the state variable. So this basically checks if we've actually run an Oracle service yet to update the Ethereum price. We could take this a step further and kind of check the timestamp that we updated that and logged that. If we want to have a more recent price and ensure that the price has been updated recently. For the purpose of this tutorial, that's fine. We've also got a string or a piece of text here, which if this require statement isn't met, then the whole transaction will fail and that string will be logged. We're using the functions here to get the DAI balance and get the WEF balance. We're then calculating the US dollar value of that wrapped Ethereum. So we're taking the WEF balance multiplied by the Ethereum price. Bear in mind, this assumes that both assets have 18 decimals, which they do. If you want to swap this out for another stablecoin, for example, or another cryptocurrency, you'd want to check that it has 18 decimals, or this isn't going to add it up correctly, because the total return includes the 18 decimals. We're then adding the WEF US dollar balance to the DAI balance and returning the total balance. Next, we're going to look at updating that price feed, and we've got two different functions here. There's a reason for that, and that is that on testnet, no one kind of arbitrages the prices. So what we've got is we're getting a price from the Uniswap decentralized exchange and a Chainlink price. These prices will be totally separate, and that's quite useful for testing because you can kind of adjust the price and see how that affects your portfolio. So we've got update ETH price from Uniswap. We've got the quote exact output single function, which is a function of the Uniswap contract. And that basically just gives us a quote for our transaction. The Chainlink Oracle function is very similar. We're just using this EAC aggregator proxy function to get the latest answer, which is what we basically done with Etherscan earlier. And the only complexity here is we're outputting a signed integer from the Chainlink price feed. We've got to change that to an unsigned integer so that it matches the Uniswap function. Next, we have a function to carry out a pretty standard Uniswap transaction. So buy WEF, and what we want to do with this function is take a DAI amount and purchase WEF with those tokens. So we've got a deadline, which is the block stamp plus 15 seconds. We've got a fee of 3,000, and that translates to 0.3%, which is the standard pool size. We've got a recipient address as ourselves. We've got the amount in is the amount in US dollars, which is passed through to the variable, which includes the 18 decimals we spoke about earlier. We've got the amount out minimum. We've got this set to 0, so that would open up to slippage and front running if we were using this for large transactions in the mainnet. No one's front running in testnet, so that's fine. We've also got the square root price limit, which is also set to 0. And we've got an example here of the emit event where we're going to use that myvault log event to emit the text amount in and then the value for that amount in. This is pretty standard. It will just create a transaction log where we can go in and see how much has been passed to this variable. It's quite useful for debugging more than anything. With ERC20 tokens, we actually have to approve the spend of the token by the Uniswap router. So we're going to do that by using the DAI token.approve function. And this is a function of the ERC20 token itself. We're going to pass through the Uniswap router address and for the total of the amount in. This basically says, go ahead Uniswap, you can spend these tokens as and when you see fit. We then use the iSwap router interface and we call the exact input single function down here with the parameters that we've already spoken about. Finally, we execute this refund ETH, which returns any ETH to our account. So how can we actually come up with these functions to interact with these contracts? Well, one of the things that's really useful is we can take the function name, which we can find from Etherscan and the contract address, and then we can go to GitHub. So there's lots of examples where contracts arbitrage, have a quick look at this one, where there's already people using Uniswap v3 and there's existing code to do this type of thing. Obviously this code might not be secure and it might not be audited, but we'll give you an idea of how to use these functions and what other people are doing to interact with external contracts. We then have a very similar function called SellWEF. The only difference here, instead of exact input single, we're using exact output single. So we're declaring the amount out in US dollars. Then we've got this rebalance function. This is going to form the bread and butter of our contract. This is going to be the rebalancing that kind of takes whatever kind of percentage we've got in our portfolio. So if we kind of deposit 100% stable coins, it will sell off some of them stable coins into cryptocurrency and vice versa. So we can run this whenever we want and it will rebalance the portfolio back to a 60-40 strategy. So let's have a look at this. We've got a require message.sender equals owner. Only the owner can rebalance their account. So this is a personal vault that only the owner who deployed the contract can use. It's not a great example for how DeFi should work, but it does keep it simple for the purposes of this tutorial. We've got a US dollar balance, which is just the DAI balance, and then a total balance, which is using the get total balance function we declared earlier. We can then work out the balance percentage. It's a strange way to be calculating a percentage because normally you do the US dollar balance divided by the total balance times 100. We're actually using 100 first, so we're doing the multiplication first, which is a little bit unusual, but the reason we're doing that is because we're working with integers here. And if we went down to decimals or fractions, it wouldn't actually work as a calculation. We're then going to use the event log to output that percentage. We've then got a simple if-else statement, whereas the US dollar balance is less than the target percentage, then we need to sell some WEF, otherwise we need to buy some. There's a require statement in both of these just to make sure that there's something to sell or buy. Then it executes the functions that we looked at earlier to buy or sell the WEF on the Uniswap v3. The next function we have is for the annual dividend. So I've called it annual dividend. It's actually set at a 3-minute time period currently. We've got the require, the message as a sender. We've also got the require that the block time or the block timestamp is greater than the next dividend timestamp, which was set during the constructor argument function. We then get a balance, which is the DAI stablecoin balance, and we take our dividend percentage. We then use the safe transfer function, which is part of that safe ERC20 Open Zeppelin library, to transfer the owner of the contract, who is ourselves, the amount that we've calculated they are due. We then set the next dividend timestamp to be block.timestamp plus the dividend frequency. There could be a little security vulnerability here where we should probably set the next dividend timestamp before we call an external function. We've then got a close account function, and this could be optional. Obviously, it kind of reduces the usefulness of having an annual dividend, but for testing purposes, this basically just lets us remove the entire DAI and WEF balances from the accounts. We're using safe transfer again here to send the owner the complete amount. We then got a receive external payable function, and this is a default function that does absolutely nothing, except that it allows us to receive Ethereum to the contract address. So we can essentially send Ethereum to the contract address and it will be stored in the contract. We're not doing anything within this function because if we'd done anything, it would actually break the transaction. MetaMask uses a quite tight gas fee for sending transactions, and that doesn't allow us to do much within the function. The final function we've got is a function to wrap that Ethereum, so we'd have to call this after we sent the transaction. It basically takes the Ethereum balance and it uses the WEF token.deposit function, which we declared earlier, using the value of the ETH balance to wrap that Ethereum so that we can use it within the portfolio. Let's move on to testing, and I'm not going to bore you with writing unit tests for all these functions. I want to go through 3 examples of how you can use Hardhat to create really robust testing systems. So the first thing we have here is a basic test program. We're going to deploy the contracts. We get a fresh variation of the contract before each test. We're simply using Hardhat and Chai here, Chai assert. We're going to import the Hardhat runtime environment and we're going to compile the contract. We're going to deploy the contract, and then once that's deployed, we're going to get an address, and then we're going to start running our tests. So the first test is it should return the correct version. There was a state variable, we just said version equals 1 in the contract. So if this doesn't go right, then there's something very, very wrong. So let's do npx hardhat test. And pretty straightforward, we can see that our assert equals version equals 1 is correct. Now let's move on to something a little bit more interesting. I have an issue straight away here because it should return a 0 DAI balance. We're going to actually have to connect to an external contract for the DAI token for this to work. And we don't have that on a local testnet. So what I'm going to do is I'm going to create a fork of the state of the local testnet. I'm using Hardhat node and Alchemy to create this fork running on a local node. So I'm basically going to take a copy of the Kovan testnet and run it locally. So to run this, we're going to use npx hardhat node, fork, then the URL for the Alchemy API. Note it's got eth-kovan as the subdomain. Then your API key goes here. We hit enter, and we get a bunch of highly insecure accounts and private keys. That is actually running now. So if we open up our test script and we do npx hard test and then network equals local, that's going to connect to our local node, which is running this Kovan fork. And we can see actually we've got some functions coming up here. The first test passed. The second test didn't run because I didn't save the document. That's why I get paid the big bucks. Let's run that again. And we can see that both of these tests have executed well. Right, now we're going to get into a really complex example, which I think shows just what you can do with the Hardhat test environment. So what we're going to do is we're going to take the accounts that Hardhat provides. I think they've all got 1,000 Ethereum minimum or something. And then we're going to send a transaction. We're going to send some Ethereum over from the owner account to the contract itself once it's been deployed. We're then going to start calling some functions. We're going to call wrap ETH. So we're going to wrap the Ethereum that we just sent. And then we're going to update the Ethereum price on Uniswap. And then we're going to rebalance it. Then we're going to check again that our DAI balance is above 0. So let's save the file and run this again. Again, we're going to run it on a local network, which is a fork of the Kovan network, because we're using external functions here, quite a lot of external functions. And you can see we're going to transfer in the Ethereum from the owner address. It's quite nice that you can use console log as well, both in the Solidity contract and in your scripting. There you go, we've got 3 passes. I think that demonstrates how useful this test environment is. You can create really complex testing scripts. You can kind of almost create fuzzers and stuff like that. It executes quite fast. And you can really use that to improve the confidence in your own code. Now let's talk a little bit about security and auditing. So obviously the absolute best thing you can do is get an audit by a third party. There's nothing more valuable than having a second pair of eyes, look over your contract, particularly from a security perspective, and see the things you've missed and kind of go through complex situations which you might not have considered when you were developing the contract. Having said that, if that's not possible or the funds aren't available, then there's some things and some tools that we can use as well. One of my favorites is Sliver. I found it's quite complex to set up, and I could only get it working in Linux. So I'm using Windows Subsystem for Linux. And let's see if I can make this a little bit bigger. There's some instructions on my blog for how I set this up and how I installed it. Let's move into the directory, which is cd mount c shared docs James code myvault. And we're just going to do Sliver. Let's have a look at the options. There's a lot of options. I won't go through all of them. There's pretty solid documentation here, but basically it's a little bit like ESLint, where we can do sliver dot. This will compile the contract, and it's going to give you a load of errors, both on your dependencies and also on your own contract code. I think it's a little bit like ESLint as well, where kind of a lot of the things you're going to disagree with about code quality and that kind of thing. There's a lot of false positives, and then maybe a year later you actually decide that they were right all along. But it's a great tool. It's quick and easy to use, and it gives you a first indication of the real stupid stuff that you might have got wrong in your contract. So there's things like myvault is not loving my use of capital letters, which is fair enough, but not really a security vulnerability. If we scroll up, we'll see the yellow and red ones. There really is a lot. Because I got this zoomed in so much, it's not formatted very well. We can see there's things like we're ignoring the return value of the Uniswap router. There are some reentrancy type bug warnings as well, which would be worth looking into for sure. Although these are on the Open Zeppelin contracts, so more than likely they're just false positives. But like I said, if you're going to be deployed to mainnet using real funds, you want to do everything you can to make sure the code is robust and secure as possible. Obviously, once it's been deployed, you can't change it. If you've got funds available, they're going to be targeted by hackers. There's also fuzzers available, like Echidna, where you can kind of fuzz the inputs to different functions and send weird data and like integer overflows and stuff like that to try and kind of create problems. And they're great as well. And these are kind of the low-hanging fruit, if you like, of Solidity smart contract security. Having said all that, I reiterate that if you're going to be using contracts for real finances, then there's nothing quite as valuable as a third-party audit. So once we created all our unit tests and we've looked at the security of our contract and we're confident in the code quality, we start thinking about deploying our contracts to the remote test nets and main nets. So for this, we use a deploy script. Again, this is quite similar to the test script. We're going to be importing the hard hat runtime environment, also importing file systems for Node.js. And the main function here, we're going to give it a contract name. We're going to compile the contract from within the deployment script. A lot of people have this as a separate function, but I like to do it to make sure that the code is compiled every time I make changes. I'm then going to deploy the contract. I'm going to write the artifacts to an external file. This is useful for once we get into kind of Web3 and front-end stuff. The artifacts contain things like the ABI and some deployment details. Finally, from within this deployment script, I'm actually going to verify the contract on Etherscan. This is probably my favorite functionality of all time, because it means that you can, once it's deployed, you can go straight into Etherscan and start interacting with the contract using MetaMask. So let's look at how this works. I'm going to go npx hardhat run scripts -deploy. I'm going to set the network to Kovum. Let's see if this works first time. Looks like the vault's been successfully deployed to this contract address. Now the final thing is the Etherscan verification. And we successfully submit the source of the contract. Just wait on Etherscan to verify the result, and it should pop out a URL which we can visit. Oh, look at that. That is a thing of absolute beauty. Let's copy that. Let's go into our web browser, paste this in here. And here's our contract. Let's have a little play around with it. Let's go to write contract. I actually need to send some funds first. Let's send it some funds. I'll send it some Ethereum. Let's send it 0.1 Ethereum. Confirm that transaction. That's gone through. If we refresh this, we should see this balance update to 0.1. So we sent the contract 0.1 Ethereum. We can then connect our wallet to Etherscan and then wrap that Ethereum. Note that the wallet address in MetaMask needs to be the same wallet address that you've got in your credentials file. That's confirmed. And this will go back to 0 now because we've actually got a balance of ERC20 tokens. Let's reconnect our wallet. So we've wrapped our Ethereum. Now let's update the price on Uniswap. So we're going to use Uniswap Quota as an Oracle service to get that data feed. If we go into read contract, we get the ETH price. Oh, it's already updated, that's great. We can get our DAI balance here is 0. But now if we go into write contract and we rebalance the portfolio, we have 100% of our portfolio currently in WETH. Once we've executed this transaction, if it goes through successfully, if we go back into our DAI balance, once that transaction has gone through, this should increase. Get DAI balance, there we go. There we go. It's not going to be perfect because the pricing on the Ethereum testnet or the Kovum testnet isn't accurate at all on the decentralized exchanges. If we look here, we've got a price of $17,000 for ETH. And it's only 2021. That all seems to be working. Let's have a look now and see if we can take our annual dividend. It must have been gone 3 minutes since we executed the contract, or deployed the contract, sorry. So let's take our annual dividend. Confirm. We should see this DAI balance decrease. If we put the DAI token balance into our wallet in a second, that will do that now. We'll wait for that to go through. Let's just grab the token address from our contract, which was DAI address, this one here. So this is the ERC20 DAI address. Let's add that as an asset in MetaMask. So we've rebalanced our portfolio and we've taken 10% out of the portfolio. We now have to wait for a set period, 3 minutes in this case, before we can take any more funds out, or we can just close our account. I'll leave this contract up if anyone wants to have a look at it. I'll put a link to it in the blog post.